So that's hot chocolate. And it says the C is 3.75. That's pretty hot. That means once it gets hot, it stays hot for a while. In a 150 grams glass cup, and its specific heat capacity is 0.84 joules grams degrees Celsius. So that means it doesn't take much energy to make the glass hot, but it won't stay hot for very long. Which is good. You don't want the container to be hotter than the liquid inside of it, right? All right, temperature change. So T initial, 10 degrees Celsius. T final equals 45, I think there's another 0, 45 degrees Celsius. And it wants to know the molar enthalpy of combustion. So that's probably kilojoules per mole. So you've got two formulas. You've got delta H equals N delta HX. And you've got Q equals MC delta T. And then you've got the relationship between the two of them. Once you've laid down everything, the math is, well, the math should be secondary, right? Math should come a little bit easier now. So not only are you heating up the hot chocolate, though, you're heating up the glass. So you're going to have two Q's, and you're going to add them together. So this is our system. This is our surroundings. The unknown that we're looking for is found with our system, right? We're looking for this, which is part of our system, so we must have enough information to solve for Q for our surroundings. So that's what you do next. You assume it's got the specific heat, it's got the same specific heat capacity of water if you need to, and you assume it's got the same density. They don't give us density, so we're going to assume it's got the same density as water. So 500 milliliters times 1 gram per 1 milliliter is 500 grams. Don't neglect to do that step. So Q is equal to 500 times 3.75 times 45 minus 10 and then this one is 150 times 0.84 times 35. So you can get Q for both the liquid and the glass cup. So this is how much heat was transferred to our surroundings from the burning of the fuels. So Q total is the sum of these numbers. So about 70.03 kilojoules. So that's equal to our delta H, right? The heat was absorbed by the glass and the hot chocolate. H is equal to negative Q, so negative 70.03 kilojoules. Plug that into your number. We've got delta H is equal to N delta H combustion, correct? Do we know anything about our fuel? Grams. Do we know anything about the identity? So can you calculate moles? No. So we can't put in this as a molar enthalpy, right? Because we don't know moles, we know mass, which is why it says determine the enthalpy of combustion. They can't say molar enthalpy of combustion because there's no moles. So we will have to put in the only information that we know, and that is our mass. So negative 70.03 kilojoules is equal to 2.75 grams. Enthalpy of combustion for every gram of fuel burnt, you will release 25.5 kilojoules of energy.
To the surroundings?
To the surroundings, yeah. Now, why did I say release? Because it's going from the system to the surroundings. It's exothermic. So if you've got a negative sign here, that means energy is being released. If it was a positive sign, the energy is being absorbed. So this is an exothermic reaction, which makes sense because you're using it as a fuel. If you burn something and it doesn't give off heat, it's not going to heat anything up. It's not going to be a good fuel. Okay? What's the chemical formula for ethene? Actually gives it to you in the question. Tamara? Thank you. C2H4. What is the other reagent when you have combustion? C2H4 plus what? Nope. It's a combustion reaction. Oxygen. Thanks, Tamara. Oxygen. What do you make if you have complete combustion? CO2 and H2O and energy. So let's go with, do we want, does it tell you if you produce? Yes, it says it produced, oh, it warms water. So we have to decide if we're going to do water or water vapor or liquid. So I'm going back to table 5.4 on page 295. Go back to table 5.4 on 295 for a minute. The state of your product is really important in enthalpy. So it says here some values for molar enthalpies of combustion. says standard values. The products are H2O liquid and CO2 gas. So we're going to assume the same thing. We're going to do H2O liquid. All right. So, balance this. Okay, so you've got one piece of information already, right? Representing thermochemical data. You've got your molar enthalpy. How many moles of ethene gas are burned in this thermochemical reaction?
One.
How do you know it's one?
There's not a number, there's not a coefficient, so it's just one.
Yeah, so the coefficient here is 1. There's 1 mole. So you take 1 mole and you multiply it by that to get kilojoules. And that is the quantity that goes into your thermochemical equation. If this was a 2, you would take that, multiply it by 2, that would be the number that you put in. Okay? Does that make sense? All right. So, I want you to do 2 thermochemical equations. Way, like Nikita said, is to put in at the end, delta H is negative 1,381 kilojoules. Not kilojoules per mole. Never put kilojoules per mole in your thermochemical. The other way then, because heat is produced, it becomes part of your thermochemical equation, and heat was a product, so it's on the right-hand side. It is always plus, it's never negative when you put it in this way. It's always a plus, it's just another product. So energy is released, so it's a step down. Your reactants have greater stored potential energy than your products. And your kilojoules or your units, the only place for kilojoules per mole is your molar enthalpy. So in this question, they asked you to find the molar enthalpy and then represent the thermochemical data in a different way. This is a great quiz or test question, right? Because it covers multiple things, multiple things. It's going to take number 3, we're going to flip it and multiply it by 6. So we have 6PCl5 arrow, 6PCl3 plus 6Cl2. So you have to multiply the entire equation by 6.
How come we multiply it by 6?
Because up here, we want a 6.
Oh, okay.
So now we've got it, and it's on the correct side of the arrow. But what you do to your equation, you have to do to your delta H as well. So our delta H is going to be negative 125 times 6. Oh, is it? Is it going to be negative 125 times 6? It's positive now because I reversed the equation. If you reverse the equation, it was exothermic, now it's endothermic. All right, so equation number 3 is done. So if this was a handout, you would cross out equation number 3 in the book. You're not going to deal with equation number 3 now at all. It's done, it's gone. So pick something else. Anything. Why 2? Sorry? Because it was a random pick. Does it have something in it that is in the overall equation that we want? No? Really? P4010, we kind of want that one, don't we? Cal's like, oh, wait a second. I can see that now. All right, so what we're going to do is we're going to use equation number 2. Is P4010 on the correct side? No. So you're going to have to reverse it. Does it have the right coefficient? Yes. So we don't have to multiply it. So we do manipulate it. So we're going to write 2 prime. We're flipping everything. So P4010 is now on the left. P4502. Our delta H just got reversed, so it's plus 2,915 kilojoules. All right. Anything else? We've used equations 2 and 3. We have to use equations 1 and 4 still. Otherwise, they wouldn't give them to us. Is there anything there that's we need in our overall? Matt?
Fourth one?
Fourth one. Is it on the correct side?
Yeah.
Does it have the right coefficient?
No.
So what do you have to multiply everything by? 10. So 4 prime, we're going to just, always flip, multiply by 10. So 10 PCl3 plus 5O2 goes to 10 Cl3PO, and then we've got negative 267 times 10. All right, so now we have to figure out what to do with equation number 1. Yeah, Matt?
Would you rearrange it and put that and add that with Cl2 to make PCl5?
Well, we can't change it. We can't change what's in equation number 1. Tell you what, let's do this in 2 steps. Hess's law of heat summation says if we add up all 4 of these new equations, we should end up with stuff canceling out so that we only have what's underlined in red at the top. So let's do it. Everybody just watch, and then that'll help us tell us what to do with equation number 1. So, is there anything on the left of this arrow? Anything on the left of this arrow that occurs on the right side as well? The 502. These are going to cancel. They're gone, which is good because we don't have them in our overall at the top. What else do we need to get rid of? We want to keep this. We want to keep this. We want to keep this. So we want to get rid of this, and this. Some of these cancel, right? 6PCl3, 10PCl3. So that would say that would be gone. That would be 4 left. So I need to get rid of 6 Cl2s, a P4, and 4 PCl3s. So let's see, what does equation number 1 have in it? It's got a P4, it's got Cl2, and it's got PCl3. In order to cancel, what's on the right has to be on the left as well. So let's look at equation number 1. P4 is on the left, and we want it to be on the left so it cancels with the P4 there. So what we're going to do is we're going to use equation number 1. Oops. We're going to use equation number 1, and we're going to use it as it is. P4 plus 6 Cl2 goes to 4 PCl3s, and our delta H is negative 1272 kilojoules. I don't have to put a 1 prime because this is not changed, right? So now I have a Cl2 on the right, a Cl2 on the left, they cancel. My P4 cancels. My 4 PCl3s cancel. So I'm only left with the stuff that's underlined in red. So my net equation, 6 PCl5 plus P4O10 are what's on the left side of the arrow. 10 Cl3PO is what's left on the right. To figure out the delta H, we do all the math. 125 times 6 plus 2,915 minus 2,670 minus 1272.
Do we have to take the multiplication?
Yep.
So we do.
Yep. So you've got 6 times 125, so that's, what, 750?
And we're adding, right? We're not subtracting?
Correct. We're going to add all these numbers up. So you're adding those numbers plus that number. So 34, that's 8. So is it about minus 400, 300, 400?
I get negative 276.
Negative 276? Got that? Yep.
If it was a few places off, like,
I wouldn't hold it against you. Yeah. Yeah. If you tell me it's 77, that's a little bit more than a little off. All right, does that make sense? This was a hard question. Normally, you don't get 4 in a Hess's Law question. Normally, it's 2 or 3.